Our last example starts off looking a little bit different, but really it's exactly the same as our first two examples. What's different is just the phrasing of the problem. Instead of being given the two specific functions, the objective and the constraint, we have to infer what those statements are, or what those functions are. For instance, we want to maximize the product of two numbers. So the product of two numbers would be x times y if their sum must be 26. So if the sum of those two numbers must be 26, then x plus y equals 26. Or setting that equal to 0, we get x plus y minus 26 equal to 0 is our function g of xy. So now we have an objective function and a constraint function, and the process follows as it did in our previous examples. So we want to maximize our objective function, which is xy, subject to the constraint function, x plus y minus 26 is equal to 0. So we again establish this function capital F, and then distribute lambda through that expression. And then take each of our first partial derivatives. So we get each of those three partial derivatives. Again, we'll solve for x and y and substitute. So in this case, we get y equals negative lambda and x equals negative lambda, which means in place of x, we can substitute in negative lambda plus our value for y, which is again negative lambda, minus 26, and we'll also take this derivative and set it equal to 0. So what we'll get in this case will be negative lambda plus negative lambda gives us negative 2 lambda, and adding the 26 to the other side gives us equals 26, meaning that lambda will be equal to negative 13. So substituting back in, we get y equals negative 13, or positive 13. And for x, we also get negative 13, or positive 13. So we want to maximize the product of two numbers if their sum must be 26. So we get the point, our maximum, occurring at f of 13, 13, and that maximum function value to be 169.